Beats happen when two waves with very similar frequencies interfere. Let's say we have these two sinusoidal sound waves interfere with each other. When we follow the superposition principle and add up their displacements, we will get something like this. The frequencies are still there and we can still hear both tones, but because of the amplitude change, the listeners would hear periodic variations in volume, loud, soft, loud, soft, loud, soft. Here is another illustration of beats waveform. The periodic volume change is called beats. Since beats are periodic events, it has frequency. I'm not going to derive this here, but the beat frequency, the frequency of volume variation, is the difference in frequencies, the absolute value of F1 minus F2. Let's listen to two different beats. The first one is the beating from a 220 Hz A3 note and a 222 Hz tone. Their interference produces beats with a 2 Hz frequency because the difference in frequencies is 2. You will hear the volume change twice every second. This next one is the beating from a 220 Hz A3 note and a 207.65 Hz G-sharp 3 note. Their interference produces beats with 12.35 Hz frequency. This means the volume changes 12.35 times every second. The beats are happening too fast for us to follow the ups and downs in volume, but you may be able to tell that the volume fluctuates quickly and regularly. Although I'm not showing you the proof for the beat frequency equation, I want you to see this. Here I have 28 bars in this length. If this is 1 second, that means this will be 28 cycles every second. And here I have another one. This one says it's 26 cycles every second. So there are 26 bars in the same length. Now, if I make those two overlap, that means those two waves, they interfere. This is what I get. If let's say the black is the peak, so it's peak overlapping with peak, trough overlapping with trough, so we have constructive interference over here, so we hear loud sound. And over here, peaks overlapping with trough on the two sides. So we have destructive interference over here, so it's a quiet sound, and then loud, soft, loud again, which means the volume changes goes through the 2 cycles of change every second. See, 28 and 26, the difference is 2. And we can try this one here. This one has 30 bars in the same length. So let me try move this one off a little bit. If I have 30 and 28 interfere, I also get loud, soft, loud, soft. The volume change through 2 cycles every second because the difference between 28 and 30 is 2 Hz also. And let's try 26 and 30. So if I remove the 28, now I have 26 and 30 over here. How many beats, what beat frequency do you expect? We should expect, see, 4 beats every second. And let's see, I have a 25 over here. So if I do 25 and 30, I get 5 beats every second. And if I try 25 and 26, how many beats every second? 1 beat every second, right? So the beat frequency is the difference of the two frequencies. But how do the amplitudes of the waves affect their beats? When the two interfering waves have the same amplitude, at the moment when peak meets trough, the two displacements cancel completely and we get no oscillation and zero volume at that moment. A little bit later, when trough meets trough, we get a trough that is these two combined, twice as steep, and therefore a higher volume at this moment. If the two interfering waves have different amplitudes, at the moment when peak meets trough, the two displacements would not cancel completely. If we have amplitudes A1 and A2, this here would be A2 minus A1. A little bit later, when trough meets trough, we would get a deeper trough. The amplitude here would be A2 plus A1. So when two waves of similar frequencies interfere, if the waves have different amplitudes, the beat volume variation would not be as pronounced as beats produced by two waves of equal amplitudes.